Hello astronomers and welcome back. This week we're going to be talking about the terrestrial planets, the Earth-like planets. These are the rocky planets that are closer to the sun in our solar system. And want to talk about the processes that shape these surfaces, and then I'm just going to use worldwide telescope to give you a little view of what some of these surfaces look like. So when we're talking about rocky worlds, there's basically three processes that sculpt the surface. The first one is erosion due to an atmosphere. So if you have an atmosphere, that allows you to have liquid water on the surface. Liquid water on the surface gives you rain, which can cause erosion. It gives you ice, which can cause erosion, and also wind can cause erosion. So these are all processes that are dictated by the existence of some kind of atmosphere causing erosion on the surface. The perfect example of that is the planet Earth, because we have an atmosphere that allows for liquid water on the surface. The second process is volcanism. So the internal heat of the planet causes molten rock to stir around on the inside, and occasionally that busts through the surface, and that causes things like volcanoes, plate tectonics, stuff like that, and that shapes the surface of the planet. And then the last one, which is probably the most dramatic and actually the most common in terms of how it affects other planets, is asteroid impacts, so impacts from other objects. So we're going to take a minute, we're going to look at Earth first because it happens to be where we live, and then we're going to talk about those three processes that shape planetary surfaces with some examples here using worldwide telescope. So first let's start with the Earth, and the first thing we notice about the Earth is it's the only planet in the solar system that is mostly covered with liquid water. And the reason for that is because it happens to be at just the right distance from the sun, such that the atmospheric pressure that we have also allows for there to be liquid water. It's not all liquid because temperature fluctuates on the surface of the planet. So we have ice at the poles. So there's Greenland and Antarctica. So those are ice caps where the liquid water has turned into solid water. And then we also have clouds, which is or I should say we have gaseous water in the atmosphere, which can condense to cause clouds. So we have all three phases of liquid water at the surface, and those are, that means that the Earth is kind of a unique place in that it can have all three of those at the same time. The other thing our atmosphere does for us is it warms the planet. So without our surface, or without our atmosphere, we would have our surface liquid water would freeze solid. So we're not close enough to the sun to have liquid water on the surface without an atmosphere that provides something called the greenhouse effect. Now, you've heard of the greenhouse effect in relation to global climate change. Some of that is good. We have a greenhouse effect that keeps the liquid water on our surface of our planet liquid, and that's a good thing. But too much greenhouse gases, and we start to warm too much, and that's what we're facing with human-caused global climate change that you'll be reading about in your chapters this week. But some atmosphere is good, and some greenhouse gases are good. Otherwise, we wouldn't have liquid water on our surface. As it stands, the Earth is really kind of at the edge. We've gone through periods of global glaciation. We've gone through periods of warming in the past, never quite as quickly as we are now due to human-caused global climate change, but the Earth does fluctuate quite a bit because of where it happens to be. The other thing you'll notice is that you don't see very many craters on the surface of the Earth, but we do see lots of evidence of volcanism. We have, you've probably heard of the Ring of Fire around the Pacific Ocean. This is a ring of very active mountain building and volcanic regions all around here. In fact, if you come up here, you probably have heard about Mount St. Helens blowing up. That's up here in Washington. That's on that Ring of Fire. And then Hawaii is a volcanic island chain, which is still in the active process of forming. In fact, there are active volcanoes on Hawaii. So we see active volcanism on the surface, and what we don't see are lots of craters. There are some examples of craters, but they tend to be relatively small, or like this region right here, almost totally obliterated by other erosion. And because of that, we say that the surface of the Earth is young. In fact, it's very hard to find any place on the surface of the Earth, either at least any large expanse of the surface that's more than a few million years old. We can find rocks on the Earth that are 4 billion years old, but they tend to be highly modified by the processes of erosion and volcanism. Okay, so we see all three of these things on Earth. We see volcanism, we see erosion due to the atmosphere, and we also do see some evidence of craters, of asteroid impacts. However, if we look at our closest neighbor, so I'm going to click over here to the planets and go look at our moon. If we look at our closest neighbor, the moon, we see a lot of craters. So this is the face of the moon you're accustomed to seeing. This is the near side of the moon, and we see that there are craters all the way around on the far side of the moon at both poles. The surface of the moon is covered in craters. Now the moon is right next to the Earth in space, so if it's getting hit by all of these asteroids, so is the planet Earth. The only difference is that we have an atmosphere and volcanism, which has basically reordered the surface of the planet Earth, so there's no longer this evidence. But if Earth did not have an atmosphere, it would look an awful lot like the moon. And the moon also shows evidence of volcanism. These smooth areas right here, they're called mare, and they are the result of volcanic eruptions that flowed out onto the surface of the moon. And those tend to be located on the near side of the moon because of the tidal influences of the Earth. That's where the magma from those volcanic events has flowed. But you can see that there's evidence of it pretty much all over the planet, although more so on the near side than the far side. Okay, so there's our planet. I call it a planet. It's our moon. If the Earth wasn't around, it would be a planet. And as you can see, it's totally different from the Earth, even though it's at exactly the same distance from the sun. The reason for that is because it doesn't have an atmosphere. And it doesn't have an atmosphere because it's very small. It's lost its atmosphere over time. All right, so let's move in. I'm going to go into the interior planets to Earth real quick. I want to go move to Venus. And we're going to take a look at Venus. Now this is not the surface, this is not the picture of Venus you would see with your naked eye. It's actually completely cloud covered. It has an extremely thick atmosphere, but you can look through that with radar instruments and see down to the surface, and this is what we see on the surface of Venus. One thing we notice is that there aren't very many craters. In fact, a lot of these craters you're seeing are actually volcanoes, but there are some craters. Not a whole bunch, but there are some. And the other thing you see is this twisted, messy surface. This region right here, which is all twisted and wrangled, and all sorts of crazy things are going on there. And there's clearly volcanism that has occurred on Venus. Not in the same way as Earth. I don't see any kind of rings of fire or chains of volcanoes, but I definitely see resurfacing. And that resurfacing is due to volcanism. Now you might ask, why isn't it due to the atmosphere if it has such a thick atmosphere? Well, the atmosphere is so thick that it's almost like being at the bottom of the ocean, at the bottom of this thick atmosphere, and it's incredibly dense. It's about 90 times the atmosphere of our Earth, and because it's almost entirely carbon dioxide, the surface temperature is about twice as hot as a pizza oven. So this is an example of why it's bad to have greenhouse gases, because the surface of Venus is so extremely hot. But you can see that there's lots of volcanism, and because it's so hot, there's no liquid water on the surface, and because there's no liquid water on the surface, the plates, if there were any, can't slide around very easily, and so Venus every so often tends to, rather than release its internal energy through chains of volcanoes, it kind of resurfaces itself. And the last time that happened was about 700 million years ago, and that's why we don't see very many craters, because the entire surface has been resurfaced relatively recently in planetary history. The thing I find so interesting about Venus is that early on in the solar system's history, it probably wasn't too much different from the Earth. It probably had liquid water. It was only slightly warmer. It's just a little bit closer to the sun than the Earth is, about 20% closer. So it was slightly warmer, but it was warm enough that the water eventually evaporated. Once it evaporated, there was no way for plate tectonics to pull carbon dioxide out of the atmosphere. The CO2 just built up in the atmosphere and until it got so hot that it went into what we call a runaway greenhouse effect, which is what you see here. And now we have Venus, which is the hellscape it is today. Okay, but an example of a planet that does have an atmosphere, but definitely driven more by volcanism and its resurfacing, not so much by craters. If we go closer into the sun, you'll see the planet Mercury. Mercury looks an awful lot like the moon minus the maria. You can see that there are lots of craters on the surface. And again, it's very small. Because it's so close to the sun, it's very hot and it's very small, so it can't hold on to an atmosphere. And because it has no atmosphere, it's just been bombarded by craters, and there's been no evidence that those craters have been erased over time. In fact, you can even see some of these enormous craters which are left over from the formation of Mercury when it was getting smashed by lots of other debris. Okay, now moving back out from the Earth, let's go back to Mars, probably at least our favorite terrestrial planet in terms of how many times we've visited as humans, at least as our robots have visited. There is the surface of Mars. Now, in some ways, Mars is the most Earth-like terrestrial planet. It does have an atmosphere. It's very thin. It's about 1,000th the atmospheric thickness of Earth. But it does have ice caps, and those seasonal ice caps are made of water ice. The permanent ice caps are made of carbon dioxide ice because the atmosphere is mostly carbon dioxide. But it does have caps like the Earth. It does have clouds, a combination of water ice and CO2 ice clouds. It does have volcanism. In fact, it even has chains of volcanoes, so there's some kind of plate movement. Doesn't seem to be like the Earth's plates, but there's some kind of plate movement because we have these chains of volcanoes. And we do see erosion that's due to other surface processes. So there are craters, but there's also examples of material flowing out on the surface. And in fact, if I zoom in a little bit, this, by the way, this is Valles Marineris. This is a crack that happened because the surface of Mars cooled early in its history. By the way, this is about the size of the United States of America, from Florida to California, so this is enormous. If you come in and look at some of these regions, zooming in on here, you can see these features that look like material has kind of busted out of here and flowed onto the surface. In fact, you can even see some things that look like channels. Now, to put this in perspective, like, this is the state of Washington. You know, these are enormous. In fact, I should say the state of Utah, that's about the size of that. These are enormous outflow features. Seriously, something catastrophic happened, but we clearly see erosion due to that. By the way, these volcanoes, this one right here is about the size of the state of Arizona. This is Olympus Mons, and it's about 3 times taller than Everest. So these are enormous features here. And you might ask, what caused all this? And what's interesting is if you look at this volcanic region over here, if you go to the exact opposite side of the planet, you hit something called the Hellas Basin, which is this giant impact crater left over from very early on in Mars's history. And antipodal to that, on the other side of Mars, is this volcano complex. So there's some suggestion that maybe the impact radiated through and caused a weakening of the crust over here, which is allowed these volcanoes to pop up. All right, so those are the terrestrial planets with those 3 processes of erosion. We have erosion due to an atmosphere, which allows for wind erosion, water erosion, ice erosion, things like that. We have volcanism, which is due to the warm interior, melting rock, and that's interacting with the surface. And then we have impact craters, which which erode the surface because of that. And in fact, you're going to learn in your material this week that one of the ways that we determine how old a surface is by looking at how many impact craters have hit it. If you see a surface with lots and lots of impact craters, it's very, very old. If you see one with not so many, it's young. That means it's been resurfaced by some other event, some sort of other erosion event in the meantime. And it's one of the ways that we can explore planetary science without necessarily leaving the Earth's surface. All right, so those are our terrestrial planets. I hope you enjoy what we have in store for you this week, and we will see you next time.